Welcome to Talking Heads. I'm Andy Shaughnessy with the Printed Circuit Engineering Association. Here with me this afternoon is Karen Burnham, the extraordinary EMC instructor.
Who might or might not be coherent after traveling since 4 o'clock this morning.
She has jet lag. She just got here and doesn't know where she is.
Nope, not even a little bit. But I will be on the ball for when I teach tomorrow.
So you're teaching a class on fundamentals of EMC, which never seems to go away because designers and double E's just don't seem to grasp EMC like they did signal integrity.
And you know, no one taught them in school.
Right.
No one gets this in school. Everybody ends up having to learn it the hard way. And then what you really see is that once people have gone through it once, they either just run screaming and are like, I'm never doing that again. I'm going to go to a monastery in Tibet or something. Or they're like, okay, I need to get some education about this.
Right.
And then they come here, they find Rick Hartley, they find Susie Webb, they find me.
Right.
You know, and or online, we've got more resources, you know, getting out there every day. And so there's stuff out there once people know to go looking for it.
Right. What is it about EMC? Is it more physics based than circuit theory based? What is it? What is the dividing line?
So in my mind, there's EMC lives in this really annoying intersection between physics and double E.
Right.
And so just the double E doesn't get you there, but honestly, just the physics doesn't get you there either.
Right.
And you need that bridge, and that's pretty hard to do.
Right.
Or it's hard to find people who have come up thinking that way.
Right. Because you're dealing with, I guess because it's an electronic, you know, you've got the signal, that is giving out these emissions, which is a physics thing. So it is kind of the worst of both worlds.
It kind of is. And then the other problem with EMC is scale, because everything starts small, but the effects are big. And so, for instance, with simulation and modeling, you know, you have to get that like sub-millimeter level PCB simulation, but then to really find out what happens, you have to go to like a centimeter mesh size, you know, to capture something that's a few meters in dimension. And man, that is just hard to do.
Right. So what are some of the things you focus on in your fundamentals class?
Yeah, so in the fundamentals class, what I'm really looking at is what are the sources of noise? So that you can look at your design and say, do I have any major risk factors here? Because to have this is one place where EMC is actually a little bit easier than signal integrity. You need something with a little power behind it.
Right.
To get an EMC problem, because signal integrity all happens on the board.
Right.
Just the littlest things can like cause crosstalk or signal integrity problems, and it's so much more sensitive.
Right.
To have an EMC problem that shows up in an EMC chamber, for FCC testing or CISPR or ISO, one of those big tests, you kind of need something with a little more oomph to get off the board and into the larger environment.
Right.
And so, you know, but when I say a little more oomph, 100 microamps of unbalanced current.
Right.
That can do it.
Right.
But, you know, I usually don't worry about individual pin switching. I worry about a clock signal.
Right.
And then once you get into power electronics, it's just, okay, that's all EMC.
Right.
So the first thing I focus on is, where does the noise typically come from, with a big emphasis on switching noise, and then also mentioning that motors can be a problem. Then we talk about how those noise sources cause not just kind of their own noise, but all these harmonics that go into higher and higher frequencies.
Right.
And then how does that interact with structures to end up radiating? Right. Because to radiate, you have to have an antenna.
Right.
No one designed an antenna into an electric vehicle.
Right.
That's not what people thought they were doing when they put together the high voltage system.
Right.
There might be antennas here or there, but you know, for like over-the-air updates or whatever. But those are not the thing causing the problem.
Right. So, I think you probably teach like how to design something so it's not an antenna, right? You want to.
Yeah, you know, over the time that I've been doing more and more teaching, I swear, I think my message is simplifying to make fewer antennas, make more transmission lines.
Yeah.
And if you can recognize what can accidentally end up being an antenna and make a transmission line instead, because transmission lines by their nature contain fields.
Right.
They just direct them where you want them to go. They don't end up spreading out to cause mischief everywhere.
Right.
So again, if you can recognize structures that will tend to just throw noise around and structures that tend to keep it contained, make more of one and less of the other, and you're 90% of the way there.
So you're teaching them how to ID these things. So when you're starting off a design, you can say, hey, there's a potential hot spot right there.
Yeah, exactly. Like here's a place where, I should take a second look.
Okay.
Here, because I've got a clock or I've got a DC-DC that's going to pull like, a few milliamps, like 10, 20 milliamps. Yeah, that's something to pay a little extra attention to. Whereas your CMOS pins, okay, that, again, maybe for signal integrity, probably not an EMC.
Right. So what would if somebody's just getting now into studying, wanting to pay more attention to EMC, what kind of advice would you give?
Solid planes. You don't need as many grounds as the data sheet says you need. Sometimes it really is that simple, because once you have a solid ground plane somewhere on your stack up, then it's so easy to use that to make a transmission line, not an antenna. Right. Because then just any trace over that solid plane is a microstrip transmission line. Like that's you can label it that or you cannot label it that, but that's what it is. So it's going to contain those fields for you without you having to do anything. No fancy filtering, no fancy anything. Just like got that trace over that plane, nice and solid. Don't have to worry about it after that.
Right.
But when somebody hands me a design and it's got 5 or 6 different labeled grounds, I'm like, okay, we're gonna be at this for a while.
What was he said? Bruce Archambault said, "Ground is where you plant potatoes."
Right. Ground's place for carrots and potatoes.
I like that.
Bruce is the best.
Is there anything you want to add?
Let's see. So yeah, the other thing, honestly, is knowing what the requirements are, knowing what applies to your unit.
Right.
There's very little. There's no one place you can go for that answer, unfortunately. Right. But one of the things I also try and bring up, because requirements really are so fundamental, are the standards, the regulations, and everything. It's why we do what we do. At the end of the day, I do actually bring that up a little bit in my classes as well. It's like know what you actually need to test, know how your test should be set up, so you don't end up chasing problems that aren't really problems.
Right.
That's another thing that I just touched on that briefly.
Okay.
Oh wait, one thing that I've been adding in more is a concept called electromagnetic resilience.
Okay.
Have you heard of that?
No. Well, I mean, I don't know what it is. Yeah.
Okay, yeah.
Tell us about it.
So there's actually an IEEE standard. It's 1848. It's a functional safety for electromagnetics.
Okay.
And Europe especially has been doing a lot of active research on electromagnetic resilience, knowing that we can't test for everything. So if you have a safety critical system, medical is the biggest example of this, you need to design to handle interference. And again, it's the sort of thing I don't, what I'm teaching tomorrow, it's just going to be, like a few slides in there to introduce the concept of like, if you have to be thinking, this is a model for how you can approach these problems. And there is a standard out there that offers you this guidance.
Right.
A standard that I'm now chairing the working group to renew. So I'm feeling it's near dear to my heart right now.
The IEEE working group. Okay.
Yep.
Oh, that's cool.
So we'll be, it was first published in 2020.
Okay.
There was a little other thing going on that year that kind of took attention away from new IEEE standards. So I don't think it got quite as much attention as it deserved.
Right.
But it's been out there in the world. It's been being used, and so we're gonna go ahead and update it and make it better.
Well, good.
So yeah.
Well, I wish you the best of luck as a kind of the EMC evangelist.
Right.
And also, Rick Hartley and Kevin Galloway, both gave classes yesterday on EMC, and they were both standing room only.
Nice.
There were people along the wall. There wasn't a seat left.
Wow.
So maybe people are realizing that you know, they need to pay more attention to this.
It seems to be getting out there.
Yeah.
Yep.
Because, like I said, everybody's focused on signal integrity for like 20 years, and then this stuff's been radiating like crazy.
I mean, 30 megahertz to 1 gigahertz, just kind of can't ignore it. That never goes away.
Right. Well, thanks for talking to me again. It's good
no problem.
good to see you.
Thanks
and
for the invitation.
yeah, I want to hear all about your class.
We'll see how it goes.
Okay. Once again, I'm Andy Shaughnessy for Talking Heads. Thanks for watching.